Okay, welcome back. So in this video I'll be talking about the domain of a function and the range of a function. So what is the domain of a function? Now consider that if you have been given a function in the form of this one, say a quadratic function, right? If you have been given a quadratic function where fx is equal to ax squared plus bx plus c, right? Ax squared plus bx plus c. So this is the general form of a quadratic function. So what is the domain of a function? Alright, now you know that when you substitute any value of x, now if I take the number line, right? If I take the number line and I'll mark 0 here, right? My positive infinity will be in this direction and my negative infinity will be in this direction. Alright, so here in this range I'll get plus 1, plus 2 and so on, and in this range I'll get minus 1 and minus 2 and so on. Right? Now if I substitute any value between negative infinity and positive infinity, I can get any real value, right? Real value for this one, a rational value, right? So if I substitute 0, I'll get fx equals z, and if I substitute 1, I'll get if 1 equals a plus b plus c. Similarly, when I substitute minus 1, I'll get if minus 1 equals a minus b plus c, right? So actually when I do some problem like this, there's no problem because there's no limitation of the value of x, so that I can get rational real values for fx, right? So rational or real values for fx can be obtained by substituting any value if a function is in this form. But consider a function like this. If I take 1 upon this function, if I define fx to be 1 upon this function, 1 upon say ax plus b, or simply 1 upon, I'll take 2x plus 3, 2x plus 3, something like this. So when 2x plus 3 is 0, when 2x plus 3 is 0, so that means x equals minus 3 by 2 or 1.5 minus 1.5, I get 1 upon 0, which is infinity. So infinity is actually not a real or rational number, right? So what we say is that when x is minus 3 by 2, fx cannot be defined, right? If x equals infinity, infinity cannot be reached. So we think fx infinity as not a rational, neither a rational or an irrational number. It's not defined. So when x is equal to minus 3 by 2, this function is not defined. So if you have in this format fx equals ax squared plus bx plus c, or ax cubed plus bx squared plus cx plus d, or any format in which there is no limitation for x to get real values or rational values for fx, we can define this function to be x to be of any value from negative infinity to positive infinity, as well as fx as the final answer. When we substitute some value for x, fx will be between minus infinity and positive infinity. But in this case, if fx is 1 upon ax in the format 1 upon ax plus b, or 1 upon ax squared plus bx plus c, when the denominator, so we don't need actually 1 here, it can be, say, it can be also something like this. Fx can be 2x plus 3 divided by x minus 2, right? 2x plus 3 divided by x minus 2. So x can be also in this form. So you don't need the numerator to be an integer or a constant. The numerator can be some function and the denominator can also be another function. So if it is in this way, we cannot define this function also when x is equal to 2. So the domain of a function is necessary to introduce the concept in which the final function fx, to get real values or rational values to fx. So the domain of a function is defined as the set of values of the independent variable. So if you have a function like this, fx equals ax squared plus bx plus c, so the independent function is x, independent variable for which a function is defined. Now in this case, when fx is equal to x squared plus bx plus c, the individual function is x, So the set of values of the independent variable, or the set of values that x can take, for which fx can be defined, is actually infinity, from negative infinity to positive infinity. But in this case, or in this case, x cannot be defined here when it is equal to minus 3 by 2, and here when x is equal to 2. So x equals 2 should be removed from the domain of the function. So x equals minus 3 by 2 is somewhere here in the number line. So we have to remove this, and all the functions from minus 3 by 2, excluding minus 3 by 2 to minus infinity, should be taken, and excluding minus 3 by 2 to positive infinity should be taken. So we have to exclude minus 3 by 2 as a value. Similarly here, we have to exclude 2 as a value here, right? You can take values from 1.99999 to minus infinity, as well as 2.00001 to positive infinity. So domain of a function, we call the domain, right? We call the domain of the first function as follows. The domain to be the domain of the first function. First function means, what I mean is this function 2x plus 3 to be from minus infinity. You can equate it, so you need curly brackets, to minus 3 by 2. So minus 3 by 2, so we can equate to minus 3 by 2 as well. So we have to use another bracket here, a curly bracket, and union minus 3 by 2, again we can equal it to positive infinity, right? To positive infinity. So the domain of that function belongs to this range. So we put an epsilon here, probably, or in some books we call this as df, or the domain of the function df. And for the second function, we call df belongs in the range, belongs from minus infinity to 2, and from 2 to positive infinity, excluding 2, right? Excluding 2. So the domain of a function is actually necessary in many concepts of functions and in the concepts of algebra, because defining a function is necessary to get real values for the function. So if you get real values for the function, we call that function fx as the range, right? Sometimes some books call it as the image, and some books call it the range. So the range is actually the better value for fx, a better definition for fx. So fx is called the range. Fx is called the range when you get real numbers or rational numbers for x, or when the domain can be defined, when the domain is defined for any function, right? When the domain is defined for any function within a range between negative infinity and positive infinity, we call this function as the range, right? This is the range, or we call it possibly RF, and this is the domain, right? Domain is not actually this function. Domain is the values that x can take. Alright. So let's take some sample examples, right? Some examples to elaborate this concept of domain and the range. So if we have been given something like this, so let's take a function like this: y equals sin x, right? Y equals sin x. So if you have been given some function like this, now you know that if you draw the graph of y equals sin x, so that's the best way to take the domain and the range. So if you draw the graph of y equals sin x, so when it is 0, I'll take 0, 5 by 2, 5, 3 5 by 2, and 2 5, 2 5, right? And this side, minus 5 by 2, minus 5, minus 3 5 by 2, and minus 2 5, right? Minus 2 5. So if I draw the function, I know that the highest value that sin x can take is positive 1, and the lowest value that sin x can take is negative 1, right? Negative 1, I know that by definition. So when it is 0, it will be 0, so the graph will be something like this, you know, from trigonometry. So the graph will be something like this, and on this side it will be something like this. Just like this, and this. right? So the graph is something like this. So the highest value that sin x this graph can take is positive 1, and the lowest value is negative 1. So let me draw those lines, dotted lines. This is positive 1. I'll take it to be somewhere here, right? To be positive 1 here, not here. And the lowest value is negative 1. Right? The lowest value is negative 1. So pardon me if it is not actually a straight line. I just drew a rough sketch to explain you, and I am not drawing the graph of y equals sin x here. I am just explaining to you about the domain and the range. So the range of functions. So no, first of all I will describe you about the domain. The domain of function, or domain of sin x, domain of x, or domain of y, right? Domain of this function should be so that I can get any value so that y can be defined at that range, as the range. So x is the independent variable, so the set of values, what are the set of values that the independent variable can take so that y can be defined. Alright, so you know that from negative infinity radian or negative infinity degrees to positive infinity degrees or positive infinity radian, x can take any value within that range. So the range of this function should be from negative infinity to positive infinity. There are no values in which the range cannot be defined. And what is the range of this function? So the range of this function is actually the values that y can take. The values that y can take is from negative 1 to positive 1. So this is actually the range. This is the range, right? But for this function actually I can write the domain to be like this. But for some functions in which where in some points of x where x cannot be defined, I can't draw a straight line like this. So I have to exclude some points. But in this example I can color this whole number line, or the degree line, to be precise, the degree line as the range of the function. Right, as the domain of the function, and as the range of the function, this vertical section. So the range of the function Rf is now negative 1 to positive 1. Now you know that at when x equals 90, you get positive 1 here, and when x is equal to minus 270 also you get positive 1 here. So you can actually equate to positive 1. So you have to put a square bracket here, as well as when x is equal to 270, positive 270, it is equal to minus 1, and when x is equal to negative 90 or minus 90 or minus 5 by 2 radian, it's equal to minus 1. So you can also equal it to minus 1. So the domain and the range for y equals sin x will be as follows. So in this example and in this video I explained to you about the concept of domain and range. So in the next video I will be taking some more examples about the domain and range, and then I will be going to a new topic on functions. See you then.